Welcome back to Science Modelizers. Welcome back to this video. Today we are going to proceed with the Northwest Regional Mock Examination, the 2024 session, that's the March 2024 session. And we are going to be seeing 0780 Physics Part 2. Okay, so let's get started with the video. Okay, so in the previous video, we ended in the fourth question, which a mistake was omitted, that is a computational error. So in this video, I'm just going to correct it, then we proceed with the question number 5. Now an object is placed 12.0 centimeters in front of a converging lens of focal length 10 centimeters. A diverging lens of focal length 8.0 centimeters is placed 22.0 centimeters from a converging lens. So the first question was actually draw a ray diagram to represent that scenario, and the last was to calculate the distance of the final image from the diverging lens. Now in general, let me present something like this. Then here I have my lens, and here I have my diverging lens. There I have my diverging lens, and so I can assume that my object is somewhere here. So my object is there, and so a proposed ray diagram, general ray diagram for this can be that we can have something like this. That's with respect to the converging lens. So we are going to observe an image which is going to be formed somewhere here. So that's the first image. So the first image can be formed at a certain point. Then the final image, now with respect to the diverging lens, so the final image with respect to the diverging lens can be formed somewhere here. So that's going to be a general case scenario for the particular problem. So but in solving, we are actually going to deduce exactly what is going to be happening. So this is a general case scenario. It can happen to be like this, but most of the times I will prefer that you solve this problem and you draw a ray diagram. So I'm going to clean this off and we begin with the actual procedure in solving that. So as we actually saw, we have I have my converging lens, and somewhere here I have my diverging lens, and I will call this to be my object O. So this distance is 12 centimeters. So this distance is 22 centimeters. Now the first thing is we are going to find the image with respect to the convex lens. So with respect to the convex lens or the converging lens, we use the lens formula where 1 on f is equal to 1 on u plus 1 over v. So I can call this v convex, v convex, f convex. So this means that my image vc will simply be, so 1 on vc will simply be 1 all over fc minus 1 all over uc. And so this means that my vc will simply be uc fc divided by uc minus fc. And so numerical application we give, our u is 12 times the focal length, which is 10, divided by 12 minus 10, and 12 times 10 is 120, divided by 2, you give 60 centimeters. And notice that a convex lens is also known as a positive lens, so it means that the focal length is positive for a convex lens, and for a diverging lens it can be a negative lens and the focal length is negative. So here the image or the object, the image with respect to the convex lens is 60 centimeters, so it's going to be found somewhere here. Now what is the nature? Is it going to be upright or is it going to be inverted? So we can check that with the value of the magnification. So the magnification is given by negative v divided by u. So we have this to be equal to negative 60 divided by 12, which will give -5. So the -5 means that the image is inverted, so we are going to get something of this nature. Is that okay? Now, at this stage, the error that was omitted in the previous video is the image distance, which we get is 60 centimeters, which is the distance from here to the object. So that's 60 centimeters. And so I used the 60 centimeters to compute the position of the final image, which is where I made a mistake, where I actually had to calculate the object distance with respect to the diverging length, and the object distance with respect to the diverging length is simply going to be 60 minus 22. So this is the actual object distance with respect to the diverging length measured from the center right up to the point where the image is formed. So I have that this total distance is 60 and this small distance is 22. So if I take 60 minus 22, I'm going to get the object distance, which is 38 centimeters. And so from here we can now pass to the next, which is the concave, which is now the concave system. So for the concave system, since my image is the object is facing downwards, or my object is facing downwards, that's inverted, it means that with respect to the diverging length, the object distance is going to carry a negative sign, since it is on the negative part of or let's say since it is inverted. So UD will simply be -38 centimeters. And so we also get that the focal length of the diverging lens is 10 centimeters. So sorry, 8 centimeters. So we get that, and I said that the focal length of the diverging lens is negative, so I'm going to use -8 centimeters. And so from there we can now use the length formula. So the length formula, we have 1 on ft will be equal to 1 on ud plus 1 on Vd. So similarly, Vd will be equal to Ud Fd divided by Ud minus Ft. So this means my Vd will be equal to, my Ud is -38 times -8 divided by -38 minus -8. So what will be the final response? So it's going to give, so it gives -10.13. So it gives me -10.13333. So 0.13 bar, 0.133. We use 2 dp centimeters. So this is the final image with respect to the diverging length. So the image will be formed somewhere around this position. So, and we can verify if it's going to be bigger or smaller than this. Okay, so question 5 says a simple potentiometer circuit is set up as shown in the figure 2 using a uniform wire PQ of length 100 cm, which has a resistance of 4.0 ohms. The resistance of the 9.0 volts battery is negligible, so it means the internal resistance of this battery of the 9.0 volts is negligible. Okay, so what do we have now? A says that if the variable resistor R were given a value of 3.2, what will be the length Pn for the whole galvanometer deflection, that's unbalanced? We have B, if R is now made 2.0 ohms and the 1.5 volt cell and galvanometer were replaced by a voltmeter of resistance 25 ohms, what would be the reading of the voltmeter if the contacts at N were replaced at the midpoint of PQ? So somewhere at the midpoint here. Okay. State the major difference between a potentiometer and a voltmeter. Let's get the solution. Now, if the variable resistor, let's start with A, the variable resistor R were given a value of 3.2 ohms, what would be the length of Pn for a zero galvanometer deflection? So that is the setup of our potentiometer. Now, by definition, Vpn is equal to K times Lpn, where K there is what we call the potential gradient, and K is simply given by I times R, where small r is equal to the resistance per unit length of our wire. And so the resistance per unit length for the wire PQ can simply be calculated by small r, which is going to be the resistance of the wire divided by 100, and the resistance of the wire was given to be 4 ohms divided by 100 centimeters, which is equal to 0.04 ohms per centimeter. But the voltage Vpn was given to be for 1.5 volts, since we are at balance, so the potential drop across these terminals will be the potential drop across Pn at balance, since no current flows through the galvanometer. And so we have that from Ohm's law. We want to get the value of the current above, which flows through our variable resistor. So what do we see from Ohm's law? We get that E will be equal to the current I into R plus RPN. So the resistance of Pn was given, and so we get that I will be equal to 9 divided by 4 plus 3.2, and numerical application will give us 1.25 amperes as the current. And so we can now calculate the potential gradient, which is equal to 1.25 times 0.04 ohm per centimeter, which gives 0.05 volts. And from there we can deduce the length of Pn from here. So since Vpn is equal to KLPN, from there we get that Lpn will be equal to Vpn divided by K, but our K, which is our potential gradient, so it's gotten to be 0.05, and numerical application gives us 30 centimeters. Now B says if R is now made 2.0 ohms and the 1.5 volt cell and galvanometer were replaced by a voltmeter of resistance 25 ohms, what would be the reading of the voltmeter if the contact L were placed midpoint? So in this particular problem, we are assuming that we are replacing all of this by a certain voltmeter V. Okay, so let's calculate the reading of the voltmeter if this wire is placed somewhere at the midpoint. Okay, so we get that the new resistance that was given, so if R is made to be 2.0 ohm, then by definition the voltage across PQ, that's mid length, will be equal to KL at the mid length. So where this LPQ on 2 is simply the length midway, centimeters. Now from here we can deduce that LPQ is 50 centimeters since it is the midpoint, but K is equal to IR, which will be simplified to be E divided by RPQ plus R times RPQ divided by 100, since we already saw this above. And so just doing numerical application, we get that our K, our new K, will simply be 9 divided by 8 plus 4 on 10. So this gives us a potential gradient of 0.06 volts per centimeter, and at this stage we get that VPQ will simply be 0.06 times 50, which is the length, and so VPQ will be 3 volts, which is going to be the reading of our voltmeter. Okay, so the next thing which we see is states one major difference between the potentiometer and the voltmeter. So the major difference is that the potentiometer measures the EMF of a cell, whereas a voltmeter measures the terminal potential difference in the circuit. A voltmeter cannot measure the EMF of a cell, cannot. Okay, so that's question number 5. So we proceed next. So we are now going to the next section of the paper, and the first question A was an experiment to describe the Young's modulus of a given material, how to obtain the Young's modulus of a given material. So I will just proceed with the B section. So for experiments, you can study your textbooks to get what to write there. So question number 6, B and C. Figure 3 shows a bullet of mass 15 grams fired horizontally at 120 meters per second to strike a wooden block of mass 2.5 kilogram 2.5 kilogram, which is suspended freely by a light vertical thread of length 100 centimeters. Calculate A, the velocity of the block and bullet immediately after impact, and B, the kinetic energy of the block and bullet after impact, and use it to determine whether or not collision is elastic. C, we should calculate the maximum height attained by the equilibrium position by the block and the embedded bullet, and the maximum inclination of the threads to the vertical. The C part says 2-point charges x and y of values q of x is equal to plus 2 microcoulomb and q of y equal to negative 3 microcoulomb and 100 millimeters apart as shown in the figure 4. Roman 1. Sketch the electric field lines between the charges x and y. Roman 2. Determine the point on the line passing through the two particles at which the resultant field strength is 0. So let's get the proposed solution to this. Okay, so let's begin with the first part. So we are going to begin with A to calculate the velocity of the block immediately after impact. So we have our bullet which travels with a certain speed of 120 meters per second, and it hits block. It hits a block which has a mass of 2.5 kilograms. So since this is suspended freely means the initial velocity of the wood is 0. So we are going to let UB be equal to the initial velocity or initial speed, speed of bullet, and we are going to let UW to the initial velocity of wood, and so on and so forth. So the subscript W will determine the wood. So A, we have to calculate the velocity of the block and bullet immediately after impact. So once this bullet will collide with this with the block of wood, the bullet is going to be embedded within the block of wood, and they are going to move with a common velocity. And so from the law of conservation of linear momentum, we get that initially the initial momentum, that's m of the bullet times the initial velocity of the bullet plus the mass of the wood times the initial velocity of the wood should be equal to the mass of the bullet times the final velocity of the bullet plus the mass of the wood times the final velocity of the wood. But since the bullet gets embedded, it means V, the final speed of the bullet will be equal to the final speed of the wood will be equal to a certain common speed. And also, since it was suspended, the block was suspended initially, it definitely means that UW is equal to 0. So from here, we can get that MB UB will be equal to MB plus MW, all of this a factor of V, and so our V will be equal to MB UB, all of this divided by MB plus UB, sorry, MB plus MW. So numerical application needs, so it gives us the speed to be equal to the mass of the bullet, which is 15 grams, that will be 0.015 kilograms, times the speed, which is 120 meters per second, all of this divided by 0.015 plus 2.5 kilograms. So what does it give? So it gives 0.7157. So I will write it to two decimal places, that is, it will give 0.72 meters per second. Now B says we should calculate the kinetic energy of the block and bullet after impact and use it to determine whether the collision is elastic or not. Now, when collision is elastic, it means that both momentum and kinetic energy is conserved. But if it is not elastic, it simply means that energy is not conserved, the momentum will be conserved. So what we have here is, let's begin by calculating the kinetic energy of the block and the bullet immediately after impact. So immediately after impact, what we get is, we have the speed is already 0.72 meters per second, and so the kinetic energy will be the total mass, which is a half, which is going to be given by a half times the mass of the bullet plus the mass of the wood, all of these times their common speed squared. So this is going to be a half into 0.015 plus 2.5, all of these times the speed square 0.72, all of that squared. So I'm going to punch what we had above. I'm going to punch this to avoid approximation. So I'm going to punch that and use the full answer and square so that we avoid errors. Okay, so doing that, I will get I get 0.64 joules approximately. 0.64 joules. So that's what I get as the kinetic energy. Okay, so this side, I wipe this side. Okay, now that we have the kinetic energy after collision, let's verify the kinetic energy before collision to verify if they are the same, because momentum has already been conserved, so definitely it should be the same. Now here what we have is, if we calculate the kinetic energy before collision, it is only the only mass which had kinetic energy was that of the bullet, so it's going to be a half the mass of the bullet times the initial velocity of the bullet square. So it's going to be a half into 0.015 times 120 squared. So let's verify if the collision will be elastic. So it gives 216 joules. So this gives 216 joules. So we clearly see from here that the initial energy is not equal to the final kinetic energy. So it tells us that the collision is not elastic. So it is not elastic. Okay, so the next thing that we see is we have yes, we have concluded with B, so now we are at the level of C. So C says the maximum height attained above the equilibrium position by the block and embedded bullet, and the maximum inclination of the thread to the vertical. So then how then do we do to compute number one, the height? So in order for us to calculate the height, we are going to use the fact that initially the block system was at rest. The block system was at rest. So after a certain time, we have something of this nature. Our block system is somewhere up, and it has covered a total height of, let's call it h, and has made an inclination of a certain theta. This L, that's L. Now we see that let me try to represent the problem here. So let me cancel this initial part so that I represent the problem clearly and see exactly what is happening. I'm going to use my block as a small rounding. So this is the initial state. This is the initial state of our block. initially. And so when the block was now came in contact with the bullet, we had a certain inclination like this, and the block is somewhere here. Something happens to the block and the new position of the block is there. So this is the initial position of the block and this is the final position. So I'm going to consider the initial position as let's first of all start by resolving everything before we define those things. So that's the inclination. We are supposed to look for theta, and at this we are going to have a height h from the reference, so we are going to call this h. I want to define the floor as my zero potential energy level, and so it means that at this stage what we have is the length of this is L, the length of this is L, and so we can actually resolve. We see that this little length, that from this point right up to this, the one in bold, that little length, I can call it x. So x will simply be equal to L minus h. So we are going to use this to compute the maximum inclination. And so in order for us to get this height, we can conserve energy, saying that the kinetic, as this body gains kinetic energy and was moving upwards, when it reached its peak, the kinetic energy was totally converted to potential energy. So from there we can get that Ke initial is equal to Pe at that height h. So Ke at my reference point, I will call my reference point O, will be equal to the potential energy at the height h. But the kinetic energy at O is the kinetic energy of the block mass system, of the bullet mass system, and that kinetic energy we calculated to be 0.64 joules. So I'm going to replace 0.64 to be equal to mgh. So we have mgh. But remember, the mass is the total mass of the block and the bullet. So this means that the height h will simply be equal to 0.64 divided by mg. And so what do we get? 0.64. This will be divided by m, which is 2.5 plus 0.015. So we have this will be divided by 2.515 times 9.8. So we get so we have it to be 0.0259. So 0.0259 meters, and so in centimeters it's going to be about multiplied by 100, we are going to have about 2.6 centimeters. So that's the height to which it is actually raised. Okay, so at that stage we can now calculate the inclination of the thread. So the inclination of the thread, since I know that this height is 2.6 centimeters, then it means my x will be L minus h, which is going to be equal to 100 minus 2.6. So 100 minus 2.6 gives 97.4 centimeters. And so here we can now calculate our maximum inclination. So we see that this side is the adjacent side and I know the hypotenuse, so we can use the cosine of the angle theta will be equal to, let me clean this side and use this side. So here we have that the cosine of the angle theta will simply be x divided by L. which is 97.4 divided by 100. And so theta will be equal to cosine inverse of that. So that will be 0.974. Okay. So it's giving me an inclination. So it's giving me a total inclination of 13.09 degrees. That's inclination. Okay, so the C part says 2 point charges x and y of values Q of x equals 2 microcoulomb and Q of y equal negative 3 microcoulomb and 100 millimeters apart as shown in the figure 4. So those are them. We have a plus and a negative charge. So we are going to start by sketching the electric field lines between the charges x and y. So here I have charge x and here I have charge y. So this is my positive 2 microcoulomb and here is my negative 3 microcoulomb. So field lines always lay from positive charges going towards negative charges. So field lines are like this. That's A. So you can draw the number of lines you feel comfortable to draw, but field lines always enter into negative charges. So okay, so that's a diagram. That's how the diagram will look like. So we see that in between the two fields they can exist no point where the field strength is 0 between them. Now we have to determine the point on the line passing through the two particles at which the resultant field strength is 0. So since we observe that here the field strength cannot be 0 within, it means that we can have a neutral point only outside of the charges. Let us take a point, for example. So if you take this as a point, we assume that it is x meters away. It is x meters away, and so the whole distance, the distance from x to that point will be x, and the distance from y to the point will be 100 minus x. And so all we have is for the electric field strength to be 0, it means that the resultant electric field, that's E with respect to x plus E with respect to the charge y at the point P, let's call that point P, should be equal to 0. So now this means that Ex should be equal to negative Ey. So from here, we are not going to work with vectors. I'm going to use the magnitude of the fields. So this means that the magnitude of Ex should be equal to the magnitude of Ey. But remember that E is given by KQ divided by R squared. So this implies E of x will be equal to K times the charge of x, which is 2, divided by this equation, that's x squared. This will be equal to E of y, which is K times 3, all of this divided by on the distance from y right up to the point x will be 100 plus x. So here we have 100 plus x, all of that squared. Okay, so at this stage the k's can actually cancel out, and so we can find the value of x. So this means that we have 2 on x squared will be equal to 3 on 100 plus x, all of that squared. So simplifying, we have 100 plus x, all of this divided by x, all square, will be equal to 3 all over 2, from where you will have that 100 plus x, all of that on x will give us the square root of 3 on 2. So we are going to take the case of the plus or minus. Now let's compute x. So let's start with the plus. Let's take it when it is positive. So when it's positive, we use the positive value. So we have 100 plus x, our cross multiply, will be equal to x times the square root of 3 divided by 2. And so if you make x the subject, x will become 100 divided by the square root of 3 on 2 minus 1. So this means x will be equal to, so we calculate it. So this will give 444.95. So this will give 444.95 millimeters. So that's where we are going to observe a zero electric field. So it is, remember, it is 444.95 millimeters from x, and so it's going to be 544.95 millimeters from y. So that's the point where the electric field should be zero. Now if we use the negative, we are going to realize that x will be negative and distances cannot be negative, so it is cancelled. Okay, so this definitely brings us to the end of this video. Thank you for watching. Please do not forget to like, share and subscribe, and I wish you the best for the GC examinations. In our next video, we are going to see data analysis of this particular mock, and subsequently we are going to solve other mock papers in both maths, mechanics, math statistics, and further mathematics with both mechanics and statistics. So stay tuned and stay blessed. See you in the next video.